Hello, class. Recall that protons that are in different chemical environments will give rise to different signals in the NMR spectrum. For example, if we had a simple alcohol molecule here, these hydrogens are going to be at a different chemical shift than this proton because its chemical environment is different. And that is typically due to the atoms that the hydrogens are attached to. So this hydrogen here is attached to an oxygen, whereas these are attached to a carbon. Gives us a different chemical environment. Now we have trends and tables that show us these trends shown right here. Now we see in this table here, highlight some things. Try to get my laser pointer. There you go. So what we have here is methyl hydrogens, and we're only going to be interested in looking at one of the three, but you can see that this methyl group is attached to a alkyl group, and it has a chemical shift of 0.9. But look at what happens if to that carbon right there, we add a second R group. To see now how the chemical shift has changed to 1.3. If you add a third R group, it's now at 1.4. Now this has to be very clear, class, that these values right here are not absolute values. There's a wiggle room. It could be, for example, for this one right here, it could be 0.93, 0.92, 0.89. Just there's flexibility in these numbers. And what changes those numbers has to do with what R groups are attached. Different alkyl groups will give us different chemical shifts, but these are ballpark ranges. So we can see here when we have these methyl groups directly attached to a bromine versus a chlorine versus a fluorine, to see how the chemical shifts are different. Here's another table showing us differences. If we look at an alkene hydrogen, a hydrogen attached to an alkene next to an R group and two other R groups, we're at 5.3 compared to when this carbon right here that I'm pointing to only doesn't have any alkyl groups attached. It's 4.7. So we have these characteristic chemical shifts that we can use these tables to help us predict certain chemical shifts when we're looking at a molecule. But what we need to do is understand why there's these characteristics. What is causing that? We need to delve deeper because yes, we can use these tables to help us, but if we understand why these tables exist, then NMR will be a little bit easier. So causes of these different chemical shifts. Okay. So the chemical shift of a proton is also going to be governed by the electrons surrounding that nucleus. Okay. So now we're at the beginning, we were just looking at the nucleus and the protons and how those, recall that if you have a proton or a charged particle rotating really, really fast, it creates a magnetic field, right? But these hydrogen atoms that consist of a proton, they also have electrons near them. Now, when electrons start spinning really, really fast, well, they are spinning really fast, and we place those electrons in an external magnetic field, we generate what's called a local magnetic field, shown right here with the B sub LOC for local. So what we have going on here is now we have two different terms up to this point. We have the external magnetic field, which we represent like that. And that external magnetic field is coming from the NMR instrument. And then when we place our molecules in an external magnetic field, the electrons start spinning in a certain pattern, certain direction, and that generates a local magnetic field. Now, that local magnetic field is always going to oppose the local magnetic field is going to oppose the external magnetic field. So I could write it like this. Let's go to a whiteboard here. So what we have going on here is we have our local magnetic field and we have an external magnetic field. And what we have is the external magnetic field orients in that direction, and the local magnetic field is always going to oppose it, go in the opposite direction. Okay. Now, this opposition right here is going to make the nucleus of the proton do something a little different here. Okay. So recall if I had a proton, right? And we place that proton in a external magnetic field. Let's put that back down there, right? So the proton is going to feel the external magnetic field, okay? But now we have to consider that, hey, there's going to be electrons also on this proton, and that's going to generate a local magnetic field that's going to oppose the external magnetic field. And so that local magnetic field shields the nucleus from feeling the external magnetic field. So the local magnetic field is kind of like shielding it, shielding the proton. So now the proton, which is the nucleus, does not feel the full effect of the external magnetic field. So what we have now is a term called the effective magnetic field. And the effective magnetic field is the magnetic field that the proton actually feels. So let's maybe say it again. We have a proton here. We place it in an external magnetic field. And if we envision that that proton has no electrons, then that proton right here will feel 100% of that external magnetic field. But we do know there is a proton. And when you place that proton in an external magnetic field, it's going to oppose it. Okay? And what that kind of does is that generates a local magnetic field that shields the nucleus from feeling that external magnetic field. And that is called B effective. Okay? So B effective is always going to be less than the external magnetic field. The external magnetic field is going to be greater than the local magnetic field. Okay. So there is a term here called shielding. Okay. And shielding is when there's electron density around the proton and it shields the proton from the external magnetic field. And so this is one reason why when we look at an NMR spectrum, we can have protons resonating at different resonance frequencies. is because not every proton has the same amount of proton or electrons around them. So there's different shielding capabilities of these protons depending on its nearest chemical environment. So not all protons have the same not all protons have the same electron density. So every proton has a varying amount of shielding. So let's just draw an example here. Let's say I have a proton here, okay, and a proton here. Now if I have proton, we'll call that proton 1 and this proton 2 for reference sake, okay? Let's say proton 1 has a lot of electron density. Lots of electron density. So I could represent that with a lot of electron density with that red, okay? Whereas proton 2 has less electron density. So it would kind of look like this. So what we have here is because the proton 1 has more electrons, or more electron density, that proton is considered to be shielded. Where the proton 2 has less electron density, and we call that deshielded. All right. Now this shielding and deshielding is caused by what atoms are attached to the protons and what that looks like. Okay. So let's come back here, make sure we covered everything. So right here is the main ideas of why there's a difference in shielding and deshielded protons. One is the inductive effect and one is magnetic anisotropy, which we will talk about in detail shortly. Okay. But I want to make sure we understand this be effective idea. Okay. Now there's this equation shown right here at the bottom, which tells us how to calculate be effective. And that is simply you add the two. So if the external magnetic field is going up, so that's going to be a positive number. And then be local is going to oppose it, right? And that's going to be in the opposite direction. So that number, the local, is going to be a negative number. So let's write that. That's going to be a positive, and that's going to be a negative number. Okay. So what I want to show you here is the shielding and deshielding idea. Okay, so what we have here is we have proton 1 and proton 2. And I'm going to draw those molecules on this whiteboard right here. Okay, so if I have a generic, let's get that in black. If we have a generic molecule here, and I'm looking at this hydrogen right here, okay, and I compare that to this molecule right here. So we are focusing our attention on that proton and that proton. Now look at what happens here. We have an alkyl group compared to a fluorine atom. Okay? So we're going to expose these two molecules to the same external magnetic field. So we're going to have our external, right? And it's going to be exactly the same over here. Okay? Now, this proton on the left, okay, we're going to call that proton 1, so we can make sure we keep track of everything. Proton 1 and the one on the right is proton 2. Proton 1 is going to have, and we will explain this shortly, but it's going to have a lot of electron density. Okay? Whereas the hydrogen on the right, or proton 2, is going to have less electron density. So the proton 1 is going to be considered shielded. Okay? And the proton on the right is going to be deshielded. Okay? Now the local magnetic field on proton 1 is going to be larger. It's going to be larger than the local magnetic field for proton 2 because it has more electron density. So because proton 1 has more electron density, it's going to have a larger local magnetic field, which is going to oppose the external magnetic field. So what we're going to find is that the B effective for proton 1 is going to be less than the B effective for proton 2 because proton 1 is more shielded. Okay. Now, what we've learned previously is when you look at proton 1 and proton 2, which one is going to feel a stronger external magnetic field? Well, because proton 2 is deshielded, less shielding, it's going to feel more of the external magnetic field, right? So recall that the change in energy of the spin states is going to be proportional to the external magnetic field. That's what we've learned previously. But now we can say, we can change it up a little bit here and say it is proportional to the effective magnetic field. So what happens here is that proton 2 is going to have, it's going to be more deshielded. It's going to have a larger B effective, which is shown right there. So that means when we compare these two states right here, we have that state and that state. Do you see how in proton 2 the gap right here, which is the change of energy of the spin, is larger? And that is all due to the fact that that proton 2 feels more of the external magnetic field. So now, proton 2 has a larger change in energy gap, okay, much larger. And so what is that going to require? Proton 2 is going to require a higher energy photon of light to make the nuclei resonate. So it's going to have a higher chemical shift. So proton 2 is going to be, let's see how can I draw it. Let's draw it over here. Let's make sure I get it right here. So proton 2 is the fluorine CH2, and proton 1 is the R. Okay. So that is proton 1, that is proton 2. So what we can say is now we can go to our tables here, right there, and see that, hey, when you have a fluorine attached, we have a chemical shift of about 4.1. Whereas when we have an alkyl group attached, we have a chemical shift of 0.9. And the reason why that is the case is because of the shielding and deshielding. Now, I just told you that proton 1 is more shielded. But why is proton 2 deshielded? Well, it has to come back to this concept of inductive effects. Inductive effects. We see that we have a fluorine atom here, which is very, very electronegative, which is going to pull electron density towards the fluorine atom. So that's going to leave less electron density for the proton. All right? Whereas alkyl groups have a tendency to be electron donating. So it's going to be shielded. Okay? So another thing to remember is this little trick that I like to use is deshielded. Okay? Deshielded relates to protons that are downfield. D. Do you see that from this example right here? Proton 2 is deshielded, and it has a chemical shift of 4.2 ppms, which is downfield in comparison to the proton 1, which has a chemical shift of 0.9. And so that would be upfield. Okay.